Hello everyone, welcome back to Z Physics. Today we're going to be revising the nuclear atom and fundamental particles. So let's get started with Rutherford's alpha particle scattering experiments. We have a little picture here of the experimental setup. We have an alpha source which is producing alpha particles which are fired at a thin sheet of gold foil. The beam of alpha particles is quite narrow, and we have a detector over here which is normally just a microscope essentially that we can vary the angle across here from 0 to about 180 degrees. Now what did Rutherford observe? First off, he noted that most of the alpha particles were passed straight through the gold foil, and this indicated the nucleus is mostly empty space, with most of the mass concentrated in a small region, aka the nucleus. Note that very few of the particles were deflected by angles larger than 90 degrees, and this means the nucleus must have a positive charge repelling the alpha particles. If you would like to have a look at a detailed video of this with some animations, have a look at my video on this topic. I'll provide a link in the description of this video. Now let's estimate the size of the nucleus. Imagine that we have an alpha particle which is approaching the nucleus, and at some point, which is going to be the distance of closest approach, the alpha particle is going to have a speed of 0. So this alpha particle is going to come here, it's going to come here, it's going to come here, and once it's here, it will start moving backwards. We could use this distance over here essentially to try and get an estimate of the size of the nucleus. Right at that point, all of the kinetic energy of the particle gets converted to electrical potential energy. Now, Rutherford used particles which were about 7.7 mega electron volts, which essentially, if we multiply by 10 to the power of 6, so let's do that, times 10 to the 6 times the electron charge. Remember, if I can see the E, I multiply by it, so times 1.6 times 10 to the power minus 19, and this is going to give us some kinetic energy equal to approximately 1.2 times 10 to the power of minus 12 joules. So this is our initial kinetic energy. Now all of this is going to get converted to electrical potential energy, so let's do that. Our kinetic energy will be equal to our electrical potential energy. The formula for potential energy is QQ over 4 pi epsilon naught times R, not R squared, where R is this distance over here. Now all we need to do essentially is just rearrange for R, so let's do this. R will be equal to QQ over 4 pi epsilon naught, and our kinetic energy will be down here. Now our charge for one of the Q's will be 79 E, because we were using gold nuclei. In fact, even better, let's just draw this in yellow, indicating that these are indeed gold nuclei. Our other charge was an alpha particle which consists of 2 protons and 2 neutrons, so this would be equal to 2 times E, where E is the elementary charge. I'm going to be dividing that by 4 pi epsilon naught times our kinetic energy. Okay, well, let's plug in some numbers now into this equation. So it would be 79 times 2 times E squared. So that's going to be times 1.6 times 10 to the power of minus 19 squared. I've squared this because obviously I have 2 factors of E, one here and one here, so E times E is E squared, which is 1.6 times 10 to the power minus 19 squared. Now I'm going to be dividing this by 4 pi times epsilon naught, which is 8.85 times 10 to the power minus 12, multiplied by the kinetic energy, which we have just up here already calculated, 1.2 times 10 to the power of minus 12. So let's write this in here, 1.2 times 10 to the power of minus 12. And if we were to plug this into a calculator, let's say up to two significant figures, we're going to get approximately 3.0 times 10 to the power of minus 14 meters. So a really good estimate for the size of the nucleus is about 10 to the power minus 14, maybe 10 to the power of minus 15 meters. And this is how we estimate the size of the nucleus. Now, what's actually inside of a nucleus? Let's have a look at the nuclear model of the atom. The modern model of the atom consists of essentially X, where X is the chemical symbol for the element. For instance, you could have helium, the nucleus of helium, which is represented by this symbol. The number A in the upper left corner is the nucleon number. In other words, the total number of protons and neutrons. For instance, helium has a total of 4 nucleons, 2 protons, and 2 neutrons. Z is the proton number, and that's located in the lower left-hand corner. For instance, helium is element number 2, so it's going to have 2 protons. The number of neutrons can be very easily worked out using the following rule that N is equal to A minus Z. Just a little bit of revision. Keep in mind that you might come across the atomic mass unit U, which in OCR A Level Physics exams, this constant is in your formula booklet, so you don't need to remember it, but it's about 1.661 times 10 to the power of minus 27 kilograms. The nuclear size is given by the following equation. R is equal to R naught A to the power of a third. This makes sense. So R here in this equation is the radius of the nucleus. R naught is a constant. It's approximately 1.2 femtometers. Remember, femto is 10 to the power minus 15. So this really is about 1.2 times 10 to the power minus 15 meters. And A, of course, is your nucleon number. So this makes sense. Essentially, the larger your nucleon number is, the larger the radius is. When A is equal to 1, your equation becomes simply that R is equal to R naught. So you can think of this as essentially roughly the size of a hydrogen nucleus. Using the following equation, we could actually estimate the density of the nucleus. All we need to do is use the equation that density is equal to mass over volume. Now let's assume that the nucleus is a tiny sphere. If that's the case, our density will be given by mass divided by 4/3 pi r cubed. However, we've already have an equation here for r. I've highlighted it over here, so we could write down that our density rho will be equal to the mass divided by 4/3 pi times r naught A to the power of 1/3, all of it cubed. Okay, well, our density will then be equal to the mass divided by 4/3 pi r naught cubed. And if I cube A raised to the power of a third, I'm just going to get A. Now, using this equation, we could calculate the density of any nuclear matter. Now, the density of the nucleus itself is extremely high. So most nuclei have a density of approximately 10 to the power of 17. So if we're calculating the density, it's about 10 to the power of 17 kilograms per meter cubed. Remember, most of the mass of the atom is concentrated in the nucleus, so the density of the atom itself is not particularly high. It's somewhere about 1.5 kilograms per meter cubed, but the density of the nucleus itself is approximately 10 to the power of 17. So something which is really worth adding in the following equation for the density of nuclear matter is that it seems to be independent of the nucleon number A. Why is that? Well, because our density is equal to the mass divided by the volume, you can assume essentially that your mass is proportional. Let me just write this over here on the side, that your mass is proportional to the nuclear number A. This is because the mass of a proton is approximately the same as the mass of a neutron. Of course, they do differ by a few parts in 10 to the power minus 27, but they're very, very similar. Because of that, the overall mass will be a multiple of essentially the mass of the individual nucleons. So you can think of the mass of the nucleus as proportional to the nucleon number. In other words, let's call that Ka for some constant k. Our nuclear density will be Ka over 4/3 pi r0 cubed times A. And notice we can do my favorite thing in physics, which is to cancel terms out, and our nuclear density is independent of the nucleon number. So this means that the hydrogen nucleus is going to have approximately the same density as the uranium nucleus, which is going to have approximately the same density as the carbon nucleus. This also tells us that the individual protons and neutrons inside probably have a very, very similar spacing between them, regardless of which nucleus we are talking about. So let's have a deep look inside of the nucleus. Let's imagine that we have something like helium, for instance, where we have two protons. The distance between individual protons in the nucleus is of the order of 10 to the power of minus 15 meters. Because the protons are of the same charge, this means that they will experience an electrostatic repulsive force. We can calculate that force using Coulomb's law. Remember, Coulomb's law says that the force is equal to QQ all over 4 pi epsilon naught r squared. Q is just the elementary charge, so in this case that will be Q times Q, so it's going to be 1.6 times 10 to the power minus 19, all of it squared, and now we're going to be dividing this by 4 pi epsilon naught is 8.85 times 10 to the power minus 12, and our distance is tiny, so that's times 10 to the power minus 15 squared. Putting this into a calculator, we are going to get approximately 230 newtons. Now, this is an absolutely huge force which is being applied to two subatomic particles. So there's a force of 230 newtons acting on something of a mass of approximately 1.6 times 10 to the power minus 27, which would essentially create an enormous acceleration. And if this electrostatic repulsion was the only force acting, all of matter should just essentially separate and very quickly accelerate to the speed of light. Luckily, that's not the case. Let's have a look at the properties of the strong nuclear force. The very fact that matter exists means that there has to be a much stronger force which is opposing that Coulomb repulsion, and it's keeping the nucleus together. Here comes the strong nuclear force. A couple of facts. It acts on all nucleons, so that's protons and neutrons. It is a short-range force. We can see how above 3 femtometers on this graph, the force is essentially 0. It is attractive up to 3 femtometers and it is repulsive below half a femtometer. In other words, in this region over here, from 0.5 to approximately 3 femtometers, the force is attractive and it is very, very strong, keeping the protons inside the nucleus together. So far we have revised quite a lot about the nuclear atom. Let's have a look at fundamental particles as well. The first aspect that we're going to revise are antiparticles. So every particle has a corresponding antiparticle. Antiparticles have the same rest mass, and this is really important. However, they do have the opposite charge. For instance, we have an electron, which of course is negative. However, its antiparticle is known as the positron, which has the same charge but with opposite signs. So whereas the electron has a charge of minus 1.6 times 10 to the power of minus 19 coulombs, the positron is going to have a charge of plus 1.6 times 10 to the power of minus 19 coulombs. Typically, we tend to essentially write down antiparticles with a little dash on top. For instance, this over here would be an antiproton, this over here would be an antineutrino. So talking about fundamental particles and antimatter and essentially fundamental physics, we need to mention the four fundamental forces, or also known as the four fundamental interactions. Probably the first one which we've studied is the gravitational force. So let's just write down here forces which are fundamental. So the gravitational one is one of them. And this is experienced by all particles which have mass. The other fundamental interaction or fundamental force that we have studied is the electromagnetism or the electromagnetic interaction, and this is experienced by all particles which have charge. We've also included the strong nuclear force, and the strong nuclear force is experienced by all nucleons. So the strong nuclear force is experienced by all nucleons. We also have the weak nuclear force, which is responsible for beta plus and beta minus decay. We can split the subatomic particles into two main classes. One of them is hadrons. For instance, we have the Large Hadron Collider, which collides hadrons. These are particles which are affected by the strong nuclear force. Examples include protons, neutrons, and a new class of particles called mesons, which we've not talked about yet, but they basically consist of a quark and an anti-quark. The other class of particles, called leptons, are particles which are not affected by the strong nuclear force. Examples include electrons, neutrinos, and muons. So what are protons and neutrons actually made of? Well, protons and neutrons are not fundamental particles. Mesons as well, they're not fundamental. They're all made out of quarks. So a proton, for instance, consists of two up quarks and a down quark, and a neutron consists of two down quarks and an up quark. The quarks have a fractional charge, so in terms of E, an up quark is plus 2/3, a down quark is minus 1/3. These values for the quarks and the corresponding anti-quarks are given in your formula booklet. We could use them to work out the, let's say, the charge of a proton. For instance, a proton consists of two U's and a D, which would mean that the overall charge for a proton will be equal to plus 2/3 E, so that's the charge of one of the up quarks, plus 2/3 E, which is the charge of the other up quark, and then we also have a down quark which has a charge of minus 1/3 E. So this over here is the charge of the down quark. So plus 2/3 plus 2/3 is going to give us 4/3 E minus 1/3 E, which of course is going to give us 3/3, which is just plus E, and that's the charge of a proton. A neutron, on the other hand, consists of two D's and a U, and we can see over here that the charge of the neutron, on the other hand, will be, so a down quark has a charge of minus 1/3 E, so that's the charge of one down quark. The other down quark also has a charge of minus 1/3 E, and a up quark has a charge of plus 2/3 E. Minus a third is minus 2/3 E plus 2/3 E, and we can see that the neutron is going to have an overall charge of 0. Now, the final aspect which we're going to be looking at today is beta decay. There are two types of beta decay, beta plus decay and beta minus decay. Now, in both of them, you either have a proton turning into a neutron or a neutron turning into a proton. In beta plus decay, we actually have a proton which is going to turn into a neutron. Now let's balance out this equation. A proton is going to have a proton number of 1 and a neutron is going to have a proton number of 0. In each case, the nucleon number is going to be 1. Charge is not conserved at the moment. We have a proton of charge 1 or plus 1 and a neutron of overall charge of 0. So in order to balance out this equation, we're going to need a beta plus particle, which is a positron. So that's going to be plus 1, 0. We also get a little neutrino overall. The neutrino has almost no mass and has no charge, and it's not a nucleon. Remember the quark composition of the proton. So a proton was an up, and down quark, which is now turned into a neutron, which is a down, and an up quark. So in this beta plus decay, what we actually have is one of those up quarks has turned into a down quark. So another way of writing down the beta plus decay equation in terms of quark composition is an up quark, which turns into a down quark, plus we get a positron and a neutrino. Let's do the same for beta minus decay. In beta minus decay, we have a neutron which turns into a proton. Now the neutron has a proton number of 0, a nucleon number of 1, and the proton is 1, 1. We also need to balance out the charge on both sides of the equation. The overall charge on the left-hand side is 0 because the neutron has an overall charge of 0. On the right-hand side, we have a charge of plus 1. In order to turn that into a 0, we're going to need a beta minus particle, which is just an electron, like so. We also get a little anti-neutrino. Now, a good rule of thumb, this is just for pure memory to try and remember in which of those equations you actually get an antineutrino. The way I always see it, if I see a minus here, I put a little dash on top. This is just for pure memory. Now, in terms of quark compositions, once again, the neutron was a down, up, which is turned into a proton, which is a up, down. So this means that essentially we have a down quark which has turned into an up quark. We also have an electron minus 1, 0 plus a little antineutrino. Okay, folks, well, this was a pretty extensive revision lesson on all of the nuclear atom and all of fundamental particles. I've been following the OCR Physics A specification. However, as always, the physics is applicable to all exam boards. Hopefully you found this video useful. Thank you very much for watching, and I'll see you in the next video.